All right, hey, let's do the second quiz review, the one on the green paper. Sorry about the audio on the other video. I had something set up wrong, obviously, but it has now been fixed. Anyway, number one. So, how do you do this? Well, you're just taking the derivative. So, wouldn't it just be that y prime equals d dx of the 3/7 times cosine? And don't we have a rule that says um, if you're taking the derivative of a constant, then you can just pull that constant out and take the derivative of whatever is left, and then multiply by the 3/7 when you're done. So we know the derivative of cosine is going to be negative sine of x. And so we can essentially just ignore the coefficient of 3/7, differentiate cosine, and then multiply by the 3/7 when we're done, getting negative 3/7 times the sine of x. And that's it for that. I'm trying to go fast. The last video being 46 minutes, that was too long, so I'm going to go a little faster. All right, what about this one? Similar to the problems from the last worksheet, just make sure you understand that the parentheses are implied to go here. So this is a chain rule problem. We'll do the derivative of the outer function, which is cosecant. So the derivative will be negative cosecant times cotangent. And again, both of those functions will take the original input as their inputs, so 5x and 5x. And then when we're done differentiating the outer function, we got to multiply by the derivative of the inside function, which is just 5. So when all is said and done, we're looking at a final answer that's just negative 5 times the cosecant of 5x times the cotangent of 5x. And that's it for that one. For 3, this one, let's see. This one is going to be negative 3 just as a coefficient on a sine of x that is getting squared. So probably the easiest way to see this one is as a product rule problem first. We go 3 times negative 2 to get negative 6. We keep our base of sine x. This power of 2 drops down to 1. And then we chain rule out the derivative of the inner function, which is a factor of cosine. So we get a y prime that equals negative 6 sine x cosine x. And again, you could stop here and I would give you credit because I'm trying not to be too worried about the more complicated trig identities, but to remind you, or if you didn't watch the previous video, remember that there is a trig identity that says that 2 times the sine of something times the cosine of the same thing. That will always be able to break down to just the sine of the original input, but doubled. So a 2 and a sine and a cosine, all of the same thing. Those 3 ingredients make this one thing, okay? And I do see that here. I know my coefficient is a negative 6, but guess what? A negative 6 is a negative 3 times a 2. So there's my 2, and now I have a sine of x as well, and I have a cosine of x. So I do have all 3 ingredients to just let that become the sine of 2x. You just double that input. So this purple answer is definitely better than this red answer, but this red answer gets you full credit, but this purple one gets you full credit and brownie points. So yeah, moving on to 4. Okay, so 4 is just a good old chain rule problem. Again, the implied parentheses are here. So your outer function is tan. So your derivative will be the derivative of tangent, which is secant squared. Oh my gosh. Secant squared. Keep that same input of 7x squared. And now that we're done differentiating that outer function, multiply by the derivative of that inner function, which is just a 14x. And then just reorder things. You'd put the 14x in the front as a coefficient, the secant squared at the end. But that's your final answer, and it really doesn't clean up at all, so that's it. number 5. So this is a product. I hope that's obvious. We've got 2x, that's a function. We've got cotangent of x, that's a function. Now don't confuse this, number 5, with number 1. Because number 1, I did have some people look at that and they thought, okay, that's product rule. Because they saw the 3/7 and they thought of that like, okay, that's a thing. And then the cosine of x is a thing. And the deal is, you're right, you actually could do this as a product rule problem, but the derivative of 3/7 would be 0. So you would get 0 times cosine plus the 3/7 times the derivative of cosine, which is negative sine. So it's not actually wrong to look at this and think of it as a cosine. I mean, to think of it as a product row problem, but you're making it overly complicated. You get 0 plus negative 3/7 sine of x, which is just negative 3/7 sine of x. You should probably be able to look at that and recognize that that 3/7 is just a coefficient. So you just pull that 3/7 off, just do the derivative of cosine, and you're done. But notice that you wouldn't be wrong if you did it as a product rule, so whatever is more comfortable. And where were we? 5? So if we head back to 5. Now this one requires product rule because this thing involves x, and this involves x. So when you have a function involving x times another function that involves x, that's when you must do product rule. So for this, we know that our derivative is going to be derivative of the first times the second plus the first times derivative of the second. So we're going to get 2 cotangent of x and then 2x, and the derivative of cotangent is cosecant squared, negative cosecant squared. So to clean this up, you've got 2 cotangents of x, and then it's minus 2x cosecant squared x. Now the cotangent and the cosecant won't clean up in any way, but what we could do at least is factor out a 2. So we'll call this 2 times the cotangent of x minus x times the cosecant squared of x. And again, I do want you to try to keep using parentheses in each trig expression. If that means using brackets around larger expressions, then do that. But try to make sure your work is nice and neat. None of your grouping symbols are messed up. If you don't use the right grouping symbols, then you might change the meaning of your answer entirely, and obviously be marked down for that. So be careful with your notation. Very careful. Number 6. So this is probably going to want to be a quotient rule problem. Again, remember, you could always call this x times 2 sine x to the negative 1. Then you don't have a fraction anymore. But that's going to almost certainly be a more difficult way to do the problem. So I would probably say just leave it and do it as a quotient rule. And quotient rule problems are going to be derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. So y prime then for us is going to be 1 times 2 sine x. And then x times the derivative of 2 sine x, which is just 2 cosine x. And then all over 2 sine x squared. So cleaning this up, our numerator would be 2 sine x minus x times 2 cosine x. So that's silly. It would be 2x cosine x. All over. Now if we square the denominator, it's 2 sine x times 2 sine x, so it goes to 4 sine squared x. Which means I can't do much, but in the numerator at least I could factor out the 2. Just pull out a 2. This 2 goes away. So we're here now. Then I could reduce the 2 with this 4, just leaving a 2 downstairs. So my best possible answer now is sine of x minus x times cosine of x all over sine squared x. And no, I can't really make this any better. Although, could I? Maybe I changed my mind. Maybe I can. Because maybe if I divide these, that gives me 1 over sine of x, because the 1 cancels the 1. But 1 over sine of x is cosecant of x. And then if I subtract from that, I'd have an x cosine x over sine squared x. Let me kind of go off to the side. 1 second. Okay, I'm back. And what was I doing? I was trying to clean this up a little bit more because it certainly looks like I could divide that second term by sine squared, and that would be x times cosine of x all over a sine of x and a second sine of x. So when all is said and done, there's a factor of 1 down here to go with this x, then cosine of x over sine of x, and then there's a factor of 1 up here to go with this sine of x. And so it looks to me like I'm getting, in lavender, an x times a cotangent of x times 1 over sine is a cosecant. And so, like it or not, that's definitely the better answer because we did want to try to avoid trig functions in our denominator. So this could be rewritten, and by now it should be jumping out at you that we also have this common factor of cosecant. So we'll pull that guy out, get a final answer of cosecant of x times 1 minus x cotan x. Yeah, that's going to be the best final answer. That makes this maybe one of the trickier ones we would ever see. But I would expect you could handle that. If you can't handle it, then ask me about it and I'll help you. All right, that's the end of 6. Here's 7. So 7 doesn't look bad. We know that to handle a problem like number 7, which is 2 terms, you literally just do the derivative as the derivative of the first term, which is tangent of 8x. And then you just add to that the derivative of the second term, which is the cosine of 1/8 x. And again, you don't have to show the work I just showed. I'm just making sure you know that the fact that this is something plus something doesn't make it complicated. It just means you do the derivative of the first and then you do the derivative of the second. No big deal. So, starting all over, that means that y prime should just be the derivative of the tangent of 8x, derivative of tangent being secant squared. But then just remember to chain rule out the derivative of the 8x. So that gives us a factor of 8. Then we add to that the derivative of cosine, which is negative sine of the 1/8 x. And then chain rule out the derivative of the inside function, which is 1/8. And then clean this up. We'll put 8 on this as a coefficient, so it's 8 times secant squared of 8x. Then we're adding a negative, so it just becomes minus 1/8 of the sine of 1/8 x. I don't know why I did parentheses there. And can we do any better from here? Not really. What could we do? The only thing I could say is if we didn't like this fractional coefficient, then we could factor out an 8. Factor out an 8, is that what I mean? No, I mean factor out the 1/8. We could factor out a 1/8. But that would mean dividing this 8 by 8, or dividing that 8 by 1/8 and getting 64. Secant squared of 8x. And then minus sine. You still have 1/8 inside the parentheses. There's really nothing we can do about the 1/8 that's in the parentheses. by factoring out a 1/8, you now have this big coefficient of 64. That does happen to be a perfect square. So would it be worth it to call this 8 secant of 8x all squared? And again, the answer here is no. None of this is better than what we had before, honestly. So this red answer is probably as good as we're gonna get. There's nothing to worry about. Like the fact that we have that coefficient, so what? All these changes I'm making aren't really making it meaningfully better. So forget it. Keep it red. That's good enough. Moving on. Okay, what about this? Well, I would always rewrite these exponents. Just rewrite this as the cosine of an x cubed, and the whole expression is getting cubed. And that to me makes it much more obvious that what we're dealing with as our outermost function is this cubic function. And then our inner function is the cosine function. But then inside of the cosine function, there's another sort of cubing function. So we've got the three layers again, where the outside is that cubing function. Then the middle sort of layer is this blue cosine function. And then that innermost x cubed is another function. So we know that this is going to be do the derivative of the outer function. You get 3 times all the stuff squared. But then you got to chain rule out the derivative of the blue function. Then you got to chain rule out the derivative of the red. So it's differentiate the outer, then chain rule again. By the way, we're keeping this whole inside function. So this will still be cosine of an x that's cubed. But now we need the derivative of that blue function, which is negative sine of an x that is cubed. But then the derivative of this involves the chain rule of the x cubed. So that pops out a 3x squared. But there's all our pieces. And if we put all those pieces together, we'd be looking at, let's see, negative 3x squared times 3 is negative 9x squared. Now this cosine function is squared, so that would come before the sine. So it'll be negative 9x squared times cosine squared of an x that is cubed times the sine of an x that is cubed. That'll do it. That'll do it. Okay, moving on. I paused for a second because there is, something we could say here. Could we sort of force the whole 2 cosine theta sine theta? Could we force that identity here? We could, but again, I don't think it's worth it. So going to 9. All right, 9, I guess we haven't seen this before, but it's a trig function inside of a trig function, but we still just work our way out. So starting with the outermost function, derivative of cosine would be negative sine. And we leave the inner function alone, so it would be negative sine of sine. But then you have to chain rule out the derivative of the inside function, derivative of sine being cosine. But that's it. That's the answer. I have no idea how we would even start to clean this up, because this is not sine of x times sine of x. You may be tempted to say that that's sine squared. It is absolutely not. This is the sine function with the sine function inside of it. So that's a weird situation. There's no way this cleans up at all. So just happily leave that one alone and move on. Number 10. What do we got here? This cosine would be the cosine of 3x and the whole thing getting squared. Then you're multiplying that by the sine of 4x. So you should certainly see this as a product. And we know that we've got this whole function here, and then we've got this function here. So we'll start by differentiating the pink guy. and we start from the outside, so we're basically treating this like it's just an x squared. So you'd end up with 2 times some stuff to the power of 1, the stuff being cosine of 3x. But now we have to chain rule out the derivative of the cosine function, which we know is negative sine of the 3x. Now we have to chain rule out the derivative of the inside of that function, the 3x. So that chain rules out another factor of 3. All of this is just the derivative of that pink stuff. We still have to multiply by the blue thing itself. So all of that is just the first bit of the derivative. So all this stuff came from the pink, including that 3. And then we're just bringing the blue down. Now we want to add, and we want to start by or actually we just want this whole thing itself. So cosine of 3x squared. So this guy whose derivative had all those pieces before, well, we're not differentiating it this time, so we just bring that guy down. But we do need to differentiate the sine of 4x, but that's not so hard because the derivative of sine is cosine. We'll leave the 4x alone. And then just chain rule out the derivative of the 4x, which is just 4. So this time we got the pink function, not differentiated, just bring the pink function down, and then here's the blue function, differentiated. And let's see if we can clean this up in any way. I see a 2, I see a negative, I see a 3, so that's telling me my coefficient is negative 6. And then we've got a sine 3x cosine 3x. Did I miss something? Yeah, I missed the sine of the 4x. That's all part of this, so it's a lot. Now we're going to add to this. Well, it'll be cosine of 3x squared. I mean cosine squared of 3x is how we tend to say that. Then it'll be the cosine of 4x. And of course the 4 will be our coefficient. So what can we do with this? I guess nothing. There is a rule kind of like this, of course. I hesitate to even bring it up, but maybe, well, I should hesitate to bring it up because I don't even remember it. But if you had the sine of a thing times the cosine of a different thing, you guys remember alpha and beta, right? And then you add to that the cosine of the first thing times the sine of the second thing. I think that's the sum and difference identity for sine, cosine. Let me look it up before I get it wrong. Okay, yeah, got it. I was right. So all of that junk right there would become the sine of the alpha plus the beta. So do we have that going on down here? Sort of, like it kind of wants to be there, but it's just not. But we do have sine of a thing, and then sort of we have the cosine of that thing again because, well, there's 2 of them. It's cosine squared. And then we've got sine of that thing. No, it needs to be cosine. It needs to be sine cosine. So we'd grab that one. Sine cosine. Cosine sine. Yeah, so it ain't happening. So there is a different identity, but again, this is going nowhere because there's all this other stuff attached to it too. So you couldn't have sine, cosine, sine, but have another whole factor attached here, another factor here. You couldn't have a coefficient of 4 on this one and a coefficient of negative 6 on this one. It's all too much. So I want to take that opportunity maybe just to remind you that another identity that is formatted kind of like this exists. But I wouldn't hold you to it on an assessment anyway, so it's no big whoop. So the only question left is it worth factoring some junk out? So there's a sine of 3x, but no sine of 3x. There's a cosine of 3x, and there is a cosine of 3x here, so that is a common factor. Maybe we should go ahead and factor that guy out and that guy out. Then there's a sine of 4x, cosine 4x. That's not common. So there is a negative 6 and a 4 as well. So that means I don't want to lead with a negative, but I could always just switch the order here and put the negative in the middle. That would be my preference. So I'm going to factor out a 2 and a cosine of 3x. Then I'm going to open a big fat set of brackets. This thing that came second now wants to come first, so it'll be 2 cosine. We factored one of these out, so instead of cosine squared of 3x, it'll be cosine of 3x. And cosine 4x. Then this guy that came first comes second, which means we're not adding anymore, we're subtracting. And we're not subtracting 6, we're subtracting 3 because we factored out a 2. But then it'll be sine 3x, cosine 3x. Not a pretty one. Kind of a lot going on. But this would be your best answer. We kind of dealt with the negative sign cleanly. We factored out the GCF. There we are. My face is getting in the way a little bit. So there's your final answer. That's 10. How about 11? All right, 11, no big whoop. When I look at 11, I see the sign of the cube root of 3x, meaning it's the sign of a 3x that's being raised to the 1/3 power. But all that's happening on the inside, so that'll be the problem for chain rule to deal with. So if I go to differentiate, first thing I'm differentiating is just sine, which of course becomes cosine. And we don't mess with the inside at all, so 3x to the 1/3. Now we got to start chain ruling out. So we differentiated the outside, now we differentiate the inside, which would mean just doing power rule. We would do the 1/3 times the coefficient of 1, getting a 1/3. Keep the base of 3x. Then do 1/3 minus 1 to get negative 2/3. But wait, there's more, because our inner function has an inner function, the 3x, which means we'd also pop out a factor of 3. So here in navy blue you see all the pieces of our answer. And hopefully right away you notice that the 1/3 and the 3 will cancel out. You may also notice that since this has a negative exponent, it's going to go down into the denominator for us. So that means that downstairs we have a 3x to the 2/3 power, which wants to be returned to a cube root. So 2/3 would mean it's the cube root of a 3x squared, and it's the whole 3x getting squared. So that's this guy all taken care of. Put it into the denominator, turn back into a radical. My numerator would just be the cosine expression, which still wants to turn back into a radical, so it'll be cube root of 3x. So just one thing left to do. This 3x squared, you probably want to just square that and say 9x squared. So I think your best answer is to say that your cosine of the cube root of 3x, that's our expression in the numerator, and downstairs we have the cube root of a 9x squared. And I like that. That seems like a good answer. So leave it like that. And that brings us to 12, the last one. Which is similar but different. If we were going to rewrite this, then this would be the sine of a 3x, and the whole thing is going to the power of 1/3. Which means that 1/3 power represents our outer function. So as we start differentiating, we'll do the 1/3 first, giving us 1/3 as a coefficient, and our power drops down by 1 down to negative 2/3. And of course the inside function we don't touch, we just leave it as whatever it was, so the sine of 3x. But of course chain rule kicks in now. I need the derivative of the sine of 3x, which would be the cosine of 3x. But then chain rule kicks in again, because now I need the derivative of the 3x, which gives me 3. So there's all your pieces, and again, because we have a negative exponent, we know that this whole thing is going to go down into the denominator. So I need a big old fraction bar. The 1/3, of course, will send a 3 into the denominator. This negative exponent will send a sine of 3x, that whole thing, into the denominator. It now is raised to the power of positive 2/3. And then, of course, in the numerator, we have a 3 times the cosine of 3x. All right, and so from here I see that certainly these 3's cancel. And of course they should have canceled because we had the 1/3 and the 3 up here. That would have canceled anyway. So how can I clean this up? I can clean it up by leaving this cosine of 3x alone. That's about as good as it gets. But downstairs, this would be another cube root problem. So it would be the cube root of sine of 3x squared. So I guess the best way to write that is the cube root of sine squared of 3x. And that seems like the end of the road for me. That's about as simple as that's going to get. So that's it. Hopefully this is helpful. There's your answer. Yeah, that's another 31 minutes of practice problems. So study tonight. Come to me with questions tomorrow. See you then. Bye.